Okay, so today we will be discussing how to perform Laplace transformations, and it is rather powerful technique, especially for solving linear differential equations. And in the several frameworks like quantum optics, electromagnetism, electrical engineering. So anyone who is familiar with Fourier transform will benefit because the technique is similar, but the rules how you do direct and inverse transformations will be different. And here I wanna run by you a very specific example, and we need to know very little basically to solve a linear equation. So I will start by uh, the I will start by the definition of Laplace transform. So the definition will be that uh, given a function ft such that t is positive, its Laplace transform. So function in Laplace space is given by fs, and Laplace transform of this function is denoted like this. And what fs means is the integral from 0 to infinity exponent minus st ft dt. And we are interested in if this limit exists where a goes to infinity from 0 to a e minus st ft dt. So this is the definition of Laplace transform. And let's start from very simple example. So suppose we want to calculate Laplace transform for ft equal 1, t bigger or equal 0. So we just will use the definition, and we get infinity from 0 to infinity, and we have to do just this, and this will give minus 1 over s e st from 0 to a, and that's nothing else than 1 over s. So first, quite simple result. And let's look at second example, which will look on the Laplace transform of exponential function. And it's very easy to see that it's just, we will make just a shift in a variable. So let's write it down, 0 to infinity, st e a t d t, and this can be just brought to the form of previous integral a infinity uh, exponent s minus a t dt, which is 1 divided s minus a. So these two very simple examples will give us a handle on solving differential equation. like simple one, just a linear differential equation. And before moving forward, let us try and derive two simple things. So first one will be, let us show that if we are given a differential equation that uh, Laplace transform of first derivative is given by s times L f t minus f0. So at first we want to prove this. In order to prove this, let's just write the definition and see what we get. So 0 to infinity, yes, t, but now we have f derivative of t dt. Now we can do integration by part. Integration by parts. Okay, and that will give us two terms, st ft from 0 to infinity minus integral from 0 plus infinity minus s. So derivative of exponential will have minus s coming in front, st ft dt. But that just gives minus f0 plus s times L f t. Okay, so first useful result is derived, and next one is following very fast from this one by the following. So now we want to kind of derive what's the same kind of formula, but for the second derivative of. Okay, so let's notice that the second derivative is like a first derivative of the derivative of t. Uh, and then we can use a previous result, and it will just give us s L f derivative t minus f derivative 0. Now, at this point, we can use the result for s derivative t and substitute it here, and that will give us s square L f t minus s f0 minus s f derivative 0. So now, just having this much, which is not really much, we have derived, I don't know, four rules maybe, four rules. And now we will try to solve the following differential equation. So second derivative of y minus 3y, first derivative minus 10y equals to, subject to the following initial conditions. Derivative at 0 is 2. And then let's basically discuss the recipe and how to attack this kind of problems. So step one is to take the Laplace transformation of the equation on both sides. Okay. Now, once we do that, what we get? So we know that Laplace transform of the first derivative is s times y s minus y0. That's sy minus 1. So because y0 is 1, yes. Now for second derivative, we will get s squared ys minus sy0 minus derivative at 0. And we substitute values of y0 and derivative at 0, and we get s squared y minus s minus 2. Okay. So now we have to implement this in the following way. So we apply Laplace transform for on the first term and a second term minus, so 10 times Laplace transform of just a variable equals L Laplace transform of 2, right? Now, let's substitute the following values. Let's see what we get. So we get s squared y minus s minus 2 minus 3 times s y minus 1 minus 10 y equals 2 divided on s. Now, the idea is to find what is ys, and it's very easy to show that it's given by the following expression. And now something very important comes into play, and it is called partial fractions. Partial fractions. Okay. So partial fractions is kind of saying that this expression, which is at this moment, it looks scary, it can be simplified further in the following, using following ansatz. And then let's multiply the common denominator, and we get a times s minus 5 times s plus 2 plus b will have s plus 2 times s plus c will have s times s minus 5. And then what we have to do, so basically we have multiplied by denominator, we got this expression, and we can assume that this denominator is already gone. And what we have to do, we have to compare left and right side together. And the tiny trick is the following. For example, you see S here is entering into, S is here, okay, and S is here. Then S minus 5 is here, S minus 5 is here. S plus 2 is here, S plus 2 is also here. So there are at least two terms that if I put a value of that term for which the term gets 0, I'm getting rid out of 3 terms, and I'm left just with 1 term. So let me demonstrate with s equals 0 case. When s equals to 0, so we know that this will go to 0 and this will go to 0. Then we will have 2 minus 5. We will have minus 10a on the right side. Okay, that's minus 10a equals, now here, I want to put s equals 0, and I'm left just with 2. Now this shows that a equal minus 1 over 5. Fair enough. Let's do for s equal 5. Sorry, this was for s equal 0. For s equal 5, we see that these terms and the first and third terms, they won't survive. And only this term will survive, and it will give us what, 5, 5, 7, 35, 35b. 35b equals to, so we are putting 5. So 25 minus 5, the 22, right? 22. The 2, which follows that v equals 22 over 35. And now we will do the same for the last case, which is s equal minus 2. Now let's look at which terms are disappearing, this term and this term. So only this term will survive. That will give some minus 7 times 2, 14c. So we get 14c equals, so minus 2, I substitute here, 4 plus 8. 8, so I get 8, and then it follows that c is equal 4 over 7. Okay. And now the idea is to perform the inverse Laplace transform on this y(s) term. Because if we perform inverse Laplace transform on this term, we will get to original solution, which is a times L minus 1, 1 over s, plus b times L minus 1, 1s minus 5, plus s times L minus 1, inverse Laplace transform on s plus 2. Substituting the coefficients, we get the final solution, which is 1 over 5 plus 22 divided 35 exponent 5t plus 4 over 7 minus 2t. This is our final solution. This is our final solution. And we could make checks that at 0 it should give us 1. T equals 0, it should give us 1, right? T equals 0. Do we get the 1 or no? 1 over 5 plus 2 divided 35 plus 4 over 7. And that's, okay, we can give 7 here. Can give 5 here. That's like, okay. 7 minus 7 plus 22 and plus 20. I did 35, which as you can see is 1. Okay, that holds up. Second thing to check is for a derivative, and that one will be small homework for you. So to check that derivative of time 0 equals to 2. Okay. Okay, this concludes our today's lecture on Laplace transformation. Hope you enjoyed it.